Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. Hope you and your family in the best of health. Lecture for grade 8, subject chemistry, chapter number 2, lecture 12, and here is Mrs. Saira Jamal. Isotopes of carbon. This is our today topic of discussion. Carbon has three isotopes. I told you in my previous lecture, carbon 12, carbon 13, and carbon 14. If you see all the three isotopes, they have same number of electrons, 2 electrons in the first shell and 4 electrons in the outermost shell, which is also called valence shell. 6 electrons means 6 protons because number of electrons are always equal to number of protons. So all the isotopes, they have same atomic number. Same atomic number means they have same number of protons and electrons. 6 protons and 6 electrons. But they have different mass number. Isotopes have different mass number. So different mass number means mass number is the sum of number of neutrons and protons. 6 neutrons and 6 protons, so mass number for carbon 12 is 12. 7 neutrons and 6 protons, addition is 13, and 8 neutron and 6 protons is 14. So you can see, dear students, that isotopes have same atomic number, they have same number of protons but different mass number. Mass number, I told you, is sum of number of neutrons and protons. So you can see 12, 13, and 14. So mass number are different. Why the masses number are different? Due to the difference in number of neutrons. You can see 6 neutrons in first case, 7 neutrons in second case, and 8 neutrons in the third case. Protons are same, 6 protons, 6 protons, 6 protons, and electrons are also same, 6 electrons. So isotopes are the atoms of an element. Element is carbon, but it has three different atoms: carbon 12, carbon 13, and carbon 14. If you have coal, and you will see that coal contain all these three types of isotope. That coal will contain carbon 12 as well as 13 and as well as 14, but it is coal. It means element is carbon, but it has three different types of atoms. Okay. Then symbols. What are the symbols to represent the isotopes of carbon? You can see here symbol for carbon 6, atomic number 6, mass number 12. Carbon 13, atomic number 6, mass number 13. For carbon 14, atomic number 6, mass number is 14. So atomic number is same, 6, 6, 6. And mass number are different, 12, 13, and 14. Properties of carbon, different forms of carbon are black or grayish black. You can see they are black or grayish black in color, except diamond. Diamond, you know, is colorless. So, and they are solid except gray or grayish black solids, all are solid, but color is not black or grayish in all the cases because you can see diamond is colorless. They are odorless, having no smell, having no taste. They have very high melting and boiling points because solid, and diamond, you know, is the hardest substance in the world, and they are insoluble in water. Diamond is as hard as that only diamond can cut the diamond, no any other thing, no knife, no sharp thing, except diamond can cut the diamond. Then their relative abundance or natural abundance, like what is the percentage of these isotopes in atmosphere or in our surrounding. Carbon 12 is present abundantly. Like I told you, if you have bunch of coal, so in that bunch, if there are suppose 10 atoms, so out of those 10 atoms, you can see the 98.9% out of that 10%, you can see 9.8 or 9.9% will be the carbon 12, only 1.1% will be carbon 13, and 0.0001%, like it is present very rarely or in very trace amount. So this is also very less, only 1.1%. So abundant isotope is carbon 12, which is 98.9%. Like in 100, you have 98.9, out of 100, 1.1, out of 100, only 0.0001%. This carbon 14 is present. So which isotope is present abundantly or in large percentage? That is carbon 12. Then next element is chlorine. Isotopes of chlorine. Chlorine has two isotopes, chlorine 35 and chlorine 37. Number of electrons and protons, I told you they are same. So 17 negative charges mean 17 electrons, and 17 positive charges mean 17 protons are there. 18 neutrons in the first case and 20 neutrons in the second case. Number of neutrons, I told you they are different. So as number of neutrons are different, definitely mass number will also be different. So in this case, 17 plus 18 is 35. So mass number of this chlorine is 35. 17 plus 20 equal to 37. So mass number of this isotope is 37. Atomic numbers are same. Electrons are same, protons are same, but neutrons are different. So due to the difference in neutron, mass numbers are different. What is mass number? Sum of protons plus neutron. Sum of protons plus neutron is equal to mass number. How many neutrons are present in chlorine 35? 18 neutrons. And in chlorine 37, 20 neutrons. How many protons? 17 protons. And 17 protons, 17 electrons, 17 electrons. A number of electrons are and protons are same, but only difference is in the number of neutrons. Symbol, how can you represent chlorine 35 and chlorine 37? You can see atomic numbers are 17, 17 same. Mass number are different, 35 and 37. What is their natural abundance? Chlorine 35 is present in atmosphere in 17%, and chlorine 37, 25%. It means chlorine 35 is abundantly present as compared to the chlorine 37. You can also represent by Bohr models. Bohr model of chlorine 35, 2 electrons in the first shell, 8 electrons in the second shell. How many are left? 8 plus 2 are 10, so 2 or 7 are left. Those 7 electrons are present in the outermost shell. Same is the case for this one. 2 electrons in the first, 8 electrons in the second, and 7 electrons in the outermost shell. Okay, because electrons are same, only difference is in the number of neutrons. 18 neutrons in chlorine 35 and 20 neutrons in chlorine 37. What is the color of chlorine gas? It is greenish yellow or grayish yellow gas with sharp, pungent, irritating smell, like bleach. Bleach is what? Bleach is chlorine. So the smell of bleach is like the smell of chlorine. It causing pungent, irritating means it causing sharp and irritating sensation. Like it irritates you. As you when you smell the bleach, a smell of bleach irritates you. So same is the case. Chlorine is a grayish yellow gas and it has pungent, irritating smell like bleach. It is fairly soluble in water. Fairly, fair, good, excellent. So fairly means not very good. It is not very good. Its solubility is not very good in water. So just soluble, but not on a greater extent. Abundance of chlorine, as I told you that the element chlorine has two isotopes, chlorine 35 and chlorine 37. The abundance of these isotopes when they occur naturally is 75% chlorine 35 and only 25% is chlorine 37. In periodic table, if you see that all the elements, their isotopes are not mentioned in the periodic table, and the masses which are mentioned in periodic table is for chlorine is 35.5. So how they found that 35.5? Because if there are, if we have chlorine in our surrounding, as I told you that chlorine may be, that chlorine may contain chlorine 35 as well as atom chlorine 37. Both atoms may be present. Although the percentages are different, chlorine 35 is in greater percentage as compared to chlorine 37. So why they wrote 35.5 mass number of chlorine in periodic table, or how they found it? So to calculate the average, we call that mass which is mentioned in the periodic table average relative atomic mass. This is not only for chlorine but for oxygen, for hydrogen, for carbon, for all elements which have isotopes. Their average relative atomic masses are mentioned in the periodic table. So how they found that average relative atomic mass? So this is the method. 75% of chlorine 35. 75% means 75 out of 100. 75 out of 100 into mass number of chlorine 35 is 35. So when you solve it, it will give you the answer 26.25. U is for atomic mass unit. I told you this U is nowadays used instead of atomic mass unit. Okay. Then 25% is chlorine 37. We will do the same for chlorine 37. Percentage is 25%. 25% mean 25 out of 100. And mass number of chlorine 37 is 37. After solving it, you will get the answer 9.25 unified or AMU. So you got two answers. One is 26.25 and unified, and second is 9.255 unified. What will you do now? You will add these two values in the final step to find out the relative atomic mass of chlorine 26.25 unified for chlorine 35 plus 9.25 unified for chlorine 37. It will give you the answer 35.5 unified. Now, I hope you understood it that how to find out the average relative atomic masses of an element. We discussed the example of chlorine, but this is same for any element. Okay, from percentage means out of 100. So divide by 100 and multiply it with the mass number or the masses of that element or that isotope will give you the answer. Then do the same for second isotope. This is the answer. Then add the two isotopes, the masses of two isotopes or relative atomic masses of two isotopes. It will give you average relative atomic mass of chlorine. So this mass is actually mentioned in the periodic table. Got it? Next one is isotopes of uranium. Uranium, is a very radioactive isotope. It is very poisonous. It is very dangerous, very harmful. So we cannot touch it directly or we cannot use it in normal labs. So there are specific nuclear reactors where uranium is used, because even a small quantity of uranium is very dangerous. So there are three isotopes of uranium with mass number 234, 235, and 238 respectively. So symbols are uranium 234, means that atomic numbers are same, 92, 92, 92, but masses or mass numbers are different, 234, 235, and 238. Again, it means that the number of neutrons are different. That's why their masses are different. So you can see the Bohr model of uranium. In the first shell, 2 electrons are present. Second shell has 8 electrons. Third shell has 18 electrons. Fourth has 32 electrons. Fifth has 21 electrons. Sixth has 9 electrons. And seventh or outermost shell has 2 electrons. How these electrons are distributed, this you will learn inshallah in the next topic, that is the electronic configuration. But just at this level, keep this in your mind that all these electrons are distributed in shells by using the Bohr model. And inside the nucleus, you know that neutrons are present. So neutrons are different, but this structure is same for all, because number of electrons is same for all the three isotopes, and electrons are 92. Now the uranium 238, it have 92 protons in the nucleus and 146 neutrons. And in uranium 235, 92 protons and 143 neutrons are present. And in uranium 234, 92 protons but 142 neutrons are present. So you can see that 92, 92, 92 number of protons are same. Only difference is in the number of neutrons. 146 neutrons, 143 neutrons, and 142 neutrons. And if you remember, I told you the formula how to find out the number of neutrons. What was the formula? The formula is mass number minus atomic number. Number of neutrons are equal to mass number minus atomic number. Okay, so the mass number for uranium 238 is 238 minus 92, 146. 235 minus 92, 143. 234 minus 92, 142 neutrons. Got it? How to find out the number of neutrons? Mass number minus atomic number, or the number of protons. Mass number minus atomic number or number of protons. It will give you the number of neutrons. So in all these three cases, you can see the number of protons are same, electrons are same. Only difference is in the number of neutrons. Properties of uranium. What are the properties of uranium? Uranium is a hard, dense, malleable, ductile, silver, white metal. You can see in the diagram, this is the ore of uranium. Ore means the impure form of uranium. It is not only uranium, other minerals or other metals are also mixed with it, and then they are separated by different technology or method or processes, which are called metallurgical operation, and the process is called metallurgy. So by that technique, all the metals or minerals are separated from this impure uranium ore, and this is the pure uranium. You can see this is pure uranium. All the other metals and minerals are separated out. It is radioactive in nature. You can see they emit radiations. They are unstable. So those isotopes which emit radiation or which release, that's why I told you that uranium is very dangerous or toxic and poisonous. The reason is they emit radiation, and these radiations are highly penetrating and having very high energy. So those high energy and those high penetration can damage our body and can cause us many problems, especially cancer to our skin and other internal body part if it penetrate internally. So it is radioactive in nature. You can see unstable and emit radiation, and it has very high density. High density, you can see 92 electrons and then 92 protons and 142 neutrons and 43 and 46, which make them very heavy. So that's why they have high density. Natural abundance uranium-34 is present only in trace amount, or in very, you can say, rarely present, and its percentage is only 0.006%. Uranium-235 as compared to 34 is a bit more, 0.72%, and uranium-238 is present abundantly, 99.27%. Uranium-34 has how many isotopes? 92. Sorry, how many protons? 92. This is fill in the blanks in your book. How many protons? 92. Because I told you that protons and electrons are the same. 92 protons, 92 electrons. 92 protons, 92 electrons. 92 protons, 92 electrons. In all the three cases, number of protons and electrons are the same. So difference is only in the number of neutrons. In uranium-234, I told you 92 minus 234 is 142. 92 minus 235, 143. And 92 minus 238, 146 neutrons are present. So the number of neutrons are different. The number of electrons and number of protons are same. Uses of uranium. Uranium-235 is used in nuclear reactor. Very important for MCQ's point of view. Always come in paper. Which isotope of uranium is used in nuclear reactors? So out of the three isotopes, 234, 235, and 238, only uranium-235 is used in nuclear reactors. Okay, learn it and memorize it. And it is also used in atomic bombs. Atomic bombs, you have heard that, which are formed or which are prepared in nuclear reactors because they contain uranium, and you know atomic bombs, very high energy, which burn all the things in its path and destroy all the things which come in its path. So it is used in atomic bombs. The reason is it produces very large amount of energy. Atomic bombs use the uranium-235. It is also used in nuclear reactors to generate energy and to produce or to produce the weapons, okay, war weapons. The nuclear energy released by fission of 1 kilogram of uranium, as I told you that uranium-235 is used in atomic bombs and also in nuclear reactors to generate energy, and then that energy is utilized to um, produce electricity. So electricity can also be produced by using these uranium-235, and the reason is that it is producing very large amount of energy. Only 1 kilogram of uranium-235, it releases energy which is equal to 17,000 kilograms of coal, or 19,000 kilograms of coal, or 12,000 kilograms of mineral oil. If you use 12,000 kilogram of oil, or if you use 19 or 17 to 19,000 kilogram of coal, the heat or the energy which produced from these processes, they are equal to only 1 kilogram of energy. 1 kilogram uranium energy. So just imagine, instead of using that large quantity of coal, it is better to use only 1 kilogram uranium, and will give us that much high energy. Okay, so the nuclear energy released by fission. What is fission? Fission is the splitting of or breaking of atomic nuclei into smaller nuclei or into smaller atoms or nuclei. Although you have learned it in bio, binary fission, and binary fission you have you have learned that when the cell it divides into two smaller daughter cells. So same is the case. Fission means breakdown or splitting of nuclei into smaller nuclei. Big nuclei, they split or they breaks up into smaller nuclei. And but this splitting produce a large amount of energy, and then that energy is utilized, I told you, in nuclear reactors or in nuclear generators to generate electricity and also use in atomic bombs. So 1 kilogram of uranium produces how much energy? The energy equal to 17,000 to 19,000 kilogram of hard coal and 12,000 kilogram of mineral oil. What is fission or nuclear fission? I told you, a nuclear process in which a heavy nucleus. Heavy nucleus means which have many protons and neutrons in it. So 142 and 143 and 146 neutron, they are too much. So they are heavy nucleus. And this heavy nucleus, when they are bombarded with neutrons, means when a neutron is passed on or fall on a heavy nucleus of uranium 235, what happened? It will take this neutron, uranium 235 will take or absorb this neutron and will convert it into a much heavier nucleus. Initially in uranium 235, I told you it have 143 neutrons, and after absorbing this neutron, it will have now 144 neutrons. So again, it is much heavier, and due to that much heavier nuclei, this nuclei become unstable, and due to that instability, it will split or it will breaks into two smaller nuclei, and those two smaller nuclei in case of uranium 235, which converted into 236, are barium and krypton. These two nuclei are formed. Along with these two nuclei, three neutrons are also emit out or eject out. Along with these neutrons, a large amount of energy is also released, and that energy is utilized in nuclear reactors. Again, I am repeating because very important for MCQ's point of view, that when uranium 235 fission occurs, or the fission of uranium 235 will give us which products or what are produced after the fission. So what are produced? Nuclei, two nuclei, small nuclei. From this big nuclei or a heavy nuclei, two small nuclei are formed, because you can see 236 is the mass number and it has 144 neutrons, so it is very heavy. And you can see this 236 split into 141 mass number and 92 mass number. It means that the neutrons, 236 neutrons, are divided or split into 141 mass number and 92 mass number. So 236 is very high or greater mass number, and 141 and 92 are smaller mass number. So this heavy nuclei split into a lighter nuclei. Nuclei are formed, energy is released, and neutrons are formed. Okay, very important for MCQs. Smaller nuclei, neutrons plus energy. These three products are formed after the fission of uranium 235. I wrote it here: a nuclear process in which a heavy nucleus, when bombarded with neutrons, splits into two nuclei. How many nuclei? Two nuclei. One nucleus is for barium and another nucleus is for krypton. Why they said only nuclei? Why not atom? The reason is that electrons are also present in these atoms, But I told you the electrons are very small and they have very smaller masses. So we just ignore the masses of electrons and we just, you can say, we are not considering here. We just considered here the nucleuses only, or which are called nuclei. Nucleus and plural is called nuclei. But just don't think this that electrons are not here or atom. This is not atom. This is only nucleus. This is complete atom of uranium 235. But as I told you that we are ignoring electrons, so just we say nucleus or nuclei. Okay, that's why I call barium atom as barium nuclei and krypton atom as krypton nuclei. Got it? It is complete atom because atom has a proton, electrons, and neutrons all over there. Got it? So in nuclear chemistry or in nuclear chemistry language, we will call it nuclei. Two nuclei are formed, neutrons are formed, and a large amount of energy is released. Two nuclei, three neutrons, and with the release of very large amount of energy. So this process is called nuclear fission. Nuclear fission, nucleus fission, splitting of nuclei, splitting of atom, splitting of nucleus. Again, I'm repeating the same that nuclear fission. It doesn't mean that only the splitting of nuclei, splitting of atoms. Okay. The same thing when neutron is bombarded on a heavy nucleus of uranium-235, it is converted into uranium-236. It got heavy and then it split into smaller nuclei. Three neutrons, one, two, three. One is behind this energy. One, two, three neutrons, and a very large amount of energy is released. 200 mega electron volt energy is released, and I told you this energy is equal to the chemical energy of 17 to 19,000 kilograms of coal. Uranium-35 is fissile isotope. Fissile meaning that it can split into smaller molecules when a lower energy neutron is fired on it or is bombarded on it. But uranium-238 has not used in nuclear reactor. I told you before why uranium-235 is used in nuclear reactor and uranium-238 is not used. The reason is that uranium-235 has that it has odd number of neutrons, and that is 143, and uranium-238 has 146 even number of neutrons. So they say as 238 is even mass, 238 is even number, 235 is odd number. So this uranium 238 has an even mass, and odd nuclei are more fissile, or means odd electrons or odd masses are easy to split up or to break up as compared to the even number. Even number are hard to fission or to have fission reaction. That's why this property is not shown by uranium 238. It is only shown by uranium 235. Again, the same thing when neutron is bombarded on uranium-235, it is converted into uranium-236, 235 plus 1 neutron more, so 236, and then it splits into nuclei, smaller nuclei, with the emission of 3 neutrons, and a large amount of energy is released. As I told you that the uranium is used for the generation of electricity, you can see this is the reactor vessel where uranium is treated by neutrons, and when neutron is bombarded on uranium, what happened? A large amount of the uranium-235, it splits into smaller nuclei, neutrons, and energy. That energy which is released, it is passed through the water, and this water, due to that much high energy, is converted into steam. That steam has very high, the molecule has very high kinetic energy. Those high kinetic energy molecules will passed on this pipe and fall on turbine, and then rotate the turbine. This rotation of turbine then activate or start that generator. So starting generator produces electricity or electric current, which is utilized by us. And again repeating, the reactor vessel which contain uranium, and uranium is uranium-235, and it is bombarded by neutrons. A large amount of energy will release. That energy, although it is passes through this pipe, but the heat which is released out of that pipe, because the pipe got very hot, and that hot pipe will transfer energy to water, because the energy is transferred from hot body to cold body. So this hot body will transfer energy or heat to cold body, that is water. Water will convert it into steam. The steam has very high kinetic energy. They will fall on turbine, rotate the turbine, and then start the generator, and then electricity will produce. So that's how the uranium is used in the generation of electric current. Uranium-234 and uranium-238 use, although I told uranium-234 is very rare, so its use is not common. But uranium-238, although it is not used in nuclear reactor, because I told you it has even mass number, and even mass number is hard to split, or these even number neutrons are hard to split. So what happened actually, just the thing is that uranium-238 can be converted into another isotopes, and the conversion will produces some alpha particles and radiation. Those alpha particles and these gamma radiation, this symbol is for gamma. These gamma radiation and these alpha particles are used in many experiments. So for experimental point of view, uranium-238 has very importance. It has very important. But for nuclear reactor, we cannot use it because we cannot split it. How the decay of uranium-238 occur? Uranium-238, it split, not split, sorry, it changes. It changes into thorium. TH is for thorium 234, and along with the thorium, alpha particles are produced, and radiation called gamma radiations are emitted. So these gamma radiation or these alpha particles, we can use them in experiment. As I told you in the Rutherford atomic model, that the Rutherford, he produced alpha particles, although he used polonium for this purpose, but this uranium-238 can also be used for the production of alpha particles or for the generation of gamma radiations. Next topic is about the uses of isotopes. Isotopes have many applications in science, medicine, and agriculture. Some of the very important uses are as follows. Number one, radioactive iodine 131. Iodine 131 is used as a tracer in diagnosing thyroid problem. Thyroid, what is thyroid? Thyroid is a gland which is present in our neck, and this thyroid, you can see it is a butterfly shaped gland. This is the image of the normal or healthy thyroid gland, but this is the image of a swollen thyroid gland. The swollen thyroid gland will make our neck swollen, and this problem is called goiter. This disease is called goiter, and this disease is due to the hypothyroidism, or hypothyroidism, like the hormones secreted by the thyroid gland. But just what are the effects on the health of this goiter? If a person has goiter, or if we have thyroid problem, then what are the effects of thyroid problem on his health? Effects on health are fatigue, means tiredness, weight gain, obesity. They are very fatty or very obese. and trouble in sleeping. They cannot sleep properly. And these are the three problems which the patient faces. How to check problem or diagnose that the patient has problem in thyroid? Although blood tests are conducted to check out problem in thyroid gland, but there is another isotope method, that is the radioactive isotope 131 medicine or tablet has given to the patient, and then through this apparatus or to this machine, which by keeping it on the neck of the patient, this radioactive isotope, it's due to the radiation they are detected by the machine. The function of thyroid gland can be studied through computer. So iodine 131 is used to diagnose problem in the thyroid gland, either it is functioning properly or it has some problem. This is not only goiter, also maybe, God forbid, the thyroid gland cancer or any other problem. It can be diagnosed by using this iodine 131 tablet, and then by uh, detecting the radiation through the machine. Then sodium 24 is used to detect the position of blood clots. If a person has blood clot or plaque in arteries, and this you have learned it in the grade 7 about the this blood clotting or plaque in blood vessels through which the blood cannot pass through the body properly, and the patient suffer from pain, and again it may be, if it gets severe, may also cause heart attack. So sodium 24 is actually used to find out or to diagnose that either the bloodstream or the pathway of blood is blocked by the clot, or which area has the clot. So all these have been checked by using sodium 24 isotope. So sodium 24 is injected into the bloodstream, and gamma rays and beta rays which are emitted from this reaction of sodium 24 is detected by a camera or detective camera outside the body, and you can find out that either the uh, the body is functioning normally or it has a clot. This sodium 24 isotope is injected in the patient body, and then when it goes to the arteries, then it has been checked by the machine which I told you, to check by the radiation which are emitted, gamma radiation and beta radiation, they are checked by the machines. Then cobalt 60 is isotope of cobalt, and it is used to kill cancer. If a patient has, God forbid, cancer, then cobalt 60 is used to kill the cancer cells. So that part of the body is exposed to the cobalt 60 radiation, which is cancerous, and then these rays kill the cancerous cell. Iodine 121 is used to image brain. You have heard about the CT scan. CT scan is the X-ray of brain. So if a patient has any problems, if he have frequent headache or dizziness or any other mental problem, so through CT scan, or if suppose God forbid, if anyone suffer from an accident and they have trauma on head, so CT scan has conducted to check the brain is normal or it has any problem. So which isotope is used to image the brain? Iodine 121. Okay, 121 is to image brain, and iodine 131. 212 comes first, so head comes first. So iodine 121 for brain, and 131, 3 comes after 2. So 131 is used for the thyroid problem. This is just a key to learn. Then carbon 14 isotope is used to find out the pathway of carbon in photosynthesis. So to conduct this experiment, you can see that this is a fume cupboard in which the plant has placed, and the light has passed on the plant. It is called illumination. By illuminated the plant for 2 to 3 hours, they introduce first the carbon 14 isotope, which produces carbon dioxide gas. That carbon dioxide gas contain carbon 14 isotope. Okay, so that carbon dioxide is produced inside this fuming pot or fuming cupboard. It has carbon 14 isotope, so plant definitely will absorb that carbon dioxide, and due to in the presence of also we watered the plant, so water is there, carbon dioxide is there, light is there. So what will happen? The carbon dioxide will absorb by the plant, and then I told you that illuminate it for 2 to 3 hours. Illuminate it for 2 to 3 or more than 2 3 hours. What will happen? The carbon dioxide will go inside the plant or absorbed by the plant, and it will do photosynthesis. Because for photosynthesis, the plants need, I told you, water, carbon dioxide, and light. So sunlight, but this light, the artificial light, will play, will play a role of sunlight. Then after 2 3 hours, remove the fuming pot or cupboard, and then check carbon 14 by using this Geiger counter. Geiger counter is a machine or a device which can check the isotopes. So by using this Geiger counter, you can check the pathway of that carbon dioxide, that where is carbon dioxide present after um, or carbon 14 present after 2 to 3 hours. So to find out the pathway of photosynthesis, carbon 14 can be used as a tracer or as a detector. Last one is the radioactive isotopes. They are also used to find out the mechanism of a chemical reaction. What is mechanism? Mechanism is that if you say that carbon react with oxygen and it will form carbon dioxide, this is a reaction. But actually what happened, the formation of carbon dioxide does not take place in one step. It takes place in two steps. In first step, what happened? Carbon react with oxygen. Half oxygen means oxygen atom, and it first give carbon monoxide. In the first step, carbon react with oxygen and will form carbon monoxide. In the second step, this carbon monoxide react with another atom of oxygen and will form carbon dioxide. This is mechanism. The reaction which completed in more than one step, those steps we call it mechanism of reaction. And if we find out net change means by addition of these two steps. While adding the two steps, we will cut out the same terms. Okay, same terms are carbon monoxide is as a reactant in second step and as a product in first. So we will cut carbon monoxide. Then okay. After cutting carbon monoxide, because it is intermediate, we have carbon left in first step. Oxygen are half oxygen molecule in first step and half in second. Half plus half is one oxygen. And carbon monoxide cut out, so carbon dioxide is left as a product. So this is the mechanism of a reaction. Which reaction? For the production of carbon dioxide. This is the mechanism of production or formation of carbon dioxide. So radioactive isotope, like suppose if I use carbon 14 in this case, so this carbon 14 will tell us about the mechanism that first carbon 14 converted into monoxide and then it gave carbon dioxide. So again by the same thing, by the radiation, gamma radiation or beta radiation emitted by carbon 14 can be detected by the Geiger counter, and then you can identify what happened actually to the carbon 14. So mechanism of a chemical reaction can also be find out by using the isotopes. Next one is to find out the structure of a compound. We can also use isotope. You can see here I have a compound of sulfur which is called sodium thiosulfate. If I will not use sodium, it is also called thiosulfate. Thiosulfate, which has S2, 2 of sulfur, and O3, 3 oxygen. So thiosulfate, and if we use sodium also, it is Na2S2O3. So sodium thiosulfate. Sodium thiosulfate structure is this. So if we want to find out the structure of this sulfur containing compound, then we can use the isotope of sulfur. So which isotope of sulfur is used? Sulfur 35. Sulfur 35 is used to find out the structure of sulfur containing compound. We can do the same for other compounds as well. Those compounds which contain that element, we can use it for the isotope of that element as a detector or as a tracer. So sulfur can be used to find out the structure of sulfur containing compound. So all these are the uses of isotopes. The first one I told you, iodine 131 is used to diagnose thyroid problem. Sodium 24 is used to find a problem in circulatory system. Iodine 123 is used to brain X-ray, find out the or take out the image of brain or X-ray of brain. Cobalt 60 I told you is used to kill the cancer cell. Carbon 14 is used to find out the pathway of carbon in photosynthesis. Radioactive isotopes are used to find out the molecular structure, or like I told you, that is of the thiosulfate. Sulfur 35 is used to find out the structure of thiosulfate. Radioactive isotopes are also used to study the mechanism of reaction, mechanism I told you. For carbon dioxide, radioactive isotopes are also used to date rocks. Date rocks means to find out the age of rock, the age of soil, or any archaeological objects, on the mummies. All these, their age can be found out by using the radioactive isotope. This inshallah we will discuss in the next lecture. Hope you understood the lecture. Uh, if you have any problem, you can ask through WhatsApp group. Thank you.